Mobile mixer unit inspection and calibration. In this final and most important section, we'll cover the visual inspection and calibration procedures, as well as yield and within batch uniformity. We'll also cover demonstration of the mobile mixer's physical capability to produce durable concrete for exposure to freeze-thaw cycles and de-icer salts. But first off, the auditor should conduct a visual inspection of the mobile mixer unit, taking note of the condition and functionality of all the items cited on the audit checklist. Get a true impression of the truck's overall condition and the type of batching mechanisms included in this particular model. Also note the degree of automation that it features. Check the mechanical functionality by opening and closing the sand and stone gates and the cement, water, and admixture dispenser open and shut off mechanisms, ensuring that they function as required. Be sure that the aggregate gates indicator needles are set to 0 when the gates are completely closed with no aggregates trapped under the gates. Ensure that the belt and auger systems are working well without burring or audible noise that would suggest any inconsistency in speed. Ask to see all of the maintenance, inspection, and repair records for the previous 3 years, demonstrating that the unit has been maintained in good condition. The cement calibration determines the rate of cement discharge from the unit and acts as the baseline reference for the gate and flow rate settings of all other materials in any given mix design. It's therefore vital that this first step be completed accurately. Before starting the calibration process, be sure to have an ergonomically adequate system of collecting representative samples of the order of 50 to 70 kilograms in order to prevent physical injury on the part of anyone involved in the process. This means you'll likely need at least 2 physically fit individuals to conduct the calibration process. You'll also need a scale, accurate enough to weigh to the nearest 0.1 kilograms. Be sure to have a calculator in hand to compute averages of 3 consecutive weights to ensure that you're dispensing materials within CSA batch tolerance limits. Therefore, you should also have access to a copy of the most current edition of CSA A23.1, A23.2 when conducting any materials dispensing calibrations, yields, within batch uniformity measurements, and any other CSA compliance requirements with respect to the certification of a mobile concrete production unit. You should only have cement in the unit at this point of the calibration process. Your cement bin should be at least half full. Run the cement conveyor until cement is flowing at a consistent rate. This usually requires you to dispense at least 50 kilograms to get consistent flow. Then stop the cement conveyor. 0 the counter. Discharge between 50 and 70 kilograms of cement and record the counts for the quantity collected. Calculate the kilograms of material collected per count and record it. Repeat these previous 2 steps at least twice more and calculate an average. Run more if necessary until the unit demonstrates that the variance between the values in a running average of 3 is within the plus or minus 1% batch tolerance limits of Table 23 of CSA A23.1 for cementing materials. Records of historical calibrations should be reviewed annually to verify ongoing compliance with the note to Table 23. The results of your calculations will determine the rate of cement discharge in kilograms per count.
Now that you've got your cement calibrated, load your stone bin to a minimum of 2/3 capacity and be sure to secure a representative subsample of the material placed in that bin for determination of moisture content before starting your stone calibration. Note that it is best to use stone and sand that is neither excessively wet nor excessively dry for the calibration process. If historical gate setting data is available for the unit being calibrated, set your first gate setting within the lower range that would have been used historically for mixes of this nature. In the absence of historical calibration data, set the gate at 3. Get the stone flowing out of the belt consistently and stop the belt with stone evenly distributed to the tip of the belt.
0 the counter. Discharge between 50 and 70 kilograms of stone and record the counts for the quantity collected. Calculate the kilograms of material collected per count and record it. Repeat these previous two steps at least twice more and calculate an average. Run more if necessary until the unit demonstrates that the variance between the values in a running average of 3 is within the plus or minus 2% batch tolerance limits of Table 23 of CSA A23.1 for aggregates. Records of historical calibrations should be reviewed annually to verify ongoing compliance with the note to Table 23. Repeat this entire process again at gate settings spaced at two higher intervals of equal range. For example, if the first setting was 3, and your course aggregate settings typically range from around 3 all the way up to 11, then select 7 for your next gate setting and 11 for your third gate setting, and run the above steps for each of these gate settings to calculate the average discharge rate at each gate set point. Your calculations will determine the rate of stone discharge in kilograms per count.
Now that you've calibrated your cement and stone, empty your stone bin and fill your sand bin to a minimum of 2/3 capacity, and be sure to secure a representative subsample of the material placed in that bin for determination of moisture content before starting your sand calibration. Once again, remember that it's best to use sand that's neither excessively wet nor excessively dry for the calibration process. If historical gate setting data is available for the unit being calibrated, set your first gate setting within the lower range that would have been used historically for mixes typically produced by the unit. In the absence of historical calibration data, set the gate at 2. Get the sand flowing out of the belt consistently and stop the belt with sand evenly distributed to the tip of the belt.
Zero the counter. Discharge between 50 and 70 kilograms of sand and record the counts for the quantity collected. Calculate the kilograms of material collected per count and record it. Repeat these previous two steps at least twice more and calculate an average. Run more if necessary until the unit demonstrates that the variance between the values in a running average of 3 is within the plus or minus 2% batch tolerance limits of Table 23 of CSA A23.1 for aggregates. Records of historical calibrations should be reviewed annually to verify ongoing compliance with the note to Table 23. Repeat this entire process again at gate settings spaced at two higher intervals of equal range. For example, if the first setting was 2, and your sand settings typically range from around 2 all the way up to 10, then select 6 for your next gate setting and 10 for your third gate setting, and run the above steps for each one of these gate settings to calculate the average discharge rate at each gate set point. Your calculations will determine the rate of sand discharge in relation to count. Using the results from all of the previous steps and placing them in a spreadsheet or plotting them manually on some graph paper, you can determine the gate settings for each material for each mix design that you use. For example, if your 30 MPa mix design contains 320 kilograms of cement, 1,150 kilograms of stone, and 720 kilograms of sand, and looking at the results you got for each of your materials, you can determine the gate setting for each of your aggregates. First of all, remember that you established your baseline with the cement. So if you determined, say, that the flow of your cement was about 0.6 kilograms per count, and the flow rates you determined for your stone at 3 gate settings were, for example, 0.50 kilograms per count for gate setting of 3, 1.12 kilograms per count for a gate setting of 5, and 1.74 kilograms per count for a gate setting of 7. Plotting the flow rates on the vertical axis of the graph and gate settings on the horizontal axis, you should be able to draw a straight line through the 3 points. Some modern units have onboard software that will either do the calculations for you and/or show the plots on a display screen. So now that we've got our flow rates for our cement and our stone, we now repeat the process to plot our gate settings for our sand. In this case, our typical range of gate settings for sand for this particular unit are 2, 4, and 6. Now that we have all of our gate setting ranges determined for both our sand and our stone, we can now start to figure out what our settings should be for this 30 MPa mix design. Again, we're basing everything off of our cement flow rate. We determined from our calibration measurements that 0.6 kilograms of cement are dispensed for every count that our system runs. All of our mix design weights are in kilograms per cubic meter. So if we're using our cement as our baseline, we need to figure out how long that belt will need to run to dispense 320 kilograms of cement. To do so, all we have to do is take 320 kilograms of cement and divide it by the dispensing rate of our cement, which we determined to be 0.6 kilograms per count, which means we need to run the belt until our counter reaches 533 counts to dispense the amount of cement required to produce a cubic meter of this 30 MPa mix design. So now we know the belt will run for 533 counts to produce a cubic meter of this concrete design. Next, we need to figure out what gate settings we need for each of our sand and our stone to dispense the amount specified in the mix design of each of those materials in a period of 533 counts. So we need to calculate the quantity per count that each aggregate needs to be dispensed at to add up to the mix design weight per cubic meter in 533 counts. For the stone, we take the mix design weight for stone and divide it by the total number of counts that the belt will be running to produce a cubic meter of concrete, which is 1,150 kilograms per cubic meter divided by 533 counts per cubic meter. The result is we need to select a gate setting that will dispense the stone at a rate of 2.16 kilograms per count. For the sand, we do the same thing, taking the mix design weight of the sand and dividing it by the total number of counts that the belt will be running to produce a cubic meter of concrete, which is 720 kilograms of sand per cubic meter divided by 533 counts per cubic meter. The result is that we need to select a gate setting that will dispense the sand at a rate of 1.35 kilograms per count. So how do we set the gate settings to dispense our stone and sand at the rates we've just determined? By using the graphs that we plotted for each aggregate. Again, some modern units have software on board that can compute your gate settings for you, but if your unit doesn't, you can use the graphs to interpolate the gate setting you'll require to get the required flow rate that you need per count. For stone, using your stone calibration graph, go up the vertical axis until you reach 2.16 kilograms per count, and move horizontally to the right from there until you hit the plot line. Then proceed straight down from the plot line until you hit the horizontal gate setting axis and read off the value from there. You should attain a gate setting value of 8.3. For the sand, repeat the process using the sand calibration graph. Go up the vertical axis until you reach 1.35 kilograms per count and move horizontally to the right from there until you hit the plot line. Then proceed straight down from the plot line until you hit the horizontal gate setting axis and read off the value from there. You should attain a gate setting value of 4.5. So far, all we've talked about are the solid materials that go into the mix. But what about the liquids? You can't make concrete without water, but knowing how much water is going into your mix is very important, and it's limited by many factors. The general principle, though, is that you only need a certain amount of water to hydrate all the cementitious particles in the mix. Any extra water beyond that is what we call water of convenience to make the concrete easier to place and finish. But that extra water also compromises the strength and durability of the end result. So we need to limit the amount of water we put in the mix and get the convenience factor from the chemical admixtures that we put in the mix. But for now, we can control some of our water by knowing the flow rate of our water meter in liters per minute. We can assess the accuracy of the water dispenser by weighing samples of water and comparing them to the amounts that the meter indicates have been dispensed. Like all previous calibrations, you should take a minimum of 3 50-liter samples and average the results of the weights of each and confirm that each is within plus or minus 1% of the average. If not, take more samples until the running average of 3 is within those tolerance limits as stipulated in Table 23 of CSA A23.1. We put chemical admixtures in our concrete to reduce the amount of water we need to put in the mix to be able to place and finish it. We also put admixtures in to entrain air in the mix to allow it to resist damage from multiple cycles of freezing and thawing, which are amplified by the use of de-icer salts. But the air has to be in the right quantity with the right size bubbles, and they need to be spaced close enough together that they can provide a network of pressure relief from the water when it expands through the concrete as it freezes. To confirm that, we'll need to look at a hardened sample of concrete from one of the cylinders cast from the yield and within batch uniformity trials that come up later in this certification process. But for now, we just want to make sure that any admixtures used get dispensed in the right quantities over the course of the batch. Again, to do this, you should take at least 3 samples, but for practical purposes, we can limit the quantities of each sample to about 5 liters. But you need to know the density of the admixture being dispensed to run the calculations to determine if the meter reading aligns with the weighed quantity collected. The meter will give values in liters or milliliters, whereas the scale will indicate a weight in kilograms. You'll need to divide the weight of the sample retained by the density of the liquid. Densities of admixtures should be readily available from your admixture supplier. Average the results of the weights of each sample retained and confirm that each sample was dispensed within plus or minus 3% of the average. If not, take more samples until the running average of 3 is within these tolerance limits as stipulated in Table 23 of CSA A23.1. Here are a few more reminders to help ensure proper calibration. Admixture and water dispensers should be calibrated at least once every 3 months of operation, or whenever there's a question of accuracy. Admixture dispensers should be flushed clean at the end of each season, or as per manufacturer's recommendations. In order to simulate the settlement of cement in its bin over the travel time period to the job site, it is suggested that the cement bin of the unit being calibrated be filled the night before to allow for air to settle out. Once again, don't use aggregates that are significantly wet or substantially dry. Make sure you retain subsamples of each and run moisture contents before starting the calibration process and before heading out to any job site to pour concrete. You should have records of absorption rates of all aggregates going into the mix and adjust all of your batch material proportions and mix water contents accordingly. If your onboard computer does not make batch adjustments for moisture contents and absorptions, a guideline for doing so can be found in Design and Control of Concrete Mixtures, published by the Cement Association of Canada. And finally, try to simulate actual job conditions for any other factors that could influence the ultimate outcome of the delivery of a mix of concrete to the field.